So again, more on limits of a functions, formal definition of limit of a function, and then algebraic approach of evaluating limits. To define limit of a function in a precise way, we consider its intuitive definition. So again, to define limit of a function, in a precise way, we consider its intuitive definition. We recall that as x approaches a, the limit of f of x if it exists is a unique number L being approached by the values of f of x as x assumes values arbitrarily close to a, values arbitrarily close to a but not equal to a. So this is how we define limit of a function intuitively. Okay? Now, what does this mean? So let us try to gradually convert it to mathematical form so that we'll be able to define limit of a function formally. This definition implies the following. Number one, So we are going to try to convert these lines involved in the definition in terms of its equivalent forms. So first, as x approaches a, the limit of f of x, if it exists, is a unique number L, being approached by the values of f of x as x assumes values arbitrarily close to a, but not equal to a. So that means we can make the values of f of x as close as we like to the number L. To the number L by taking the values of x close enough to a but not equal to a. This line, the values of f of x as close as you like to L, what does it mean? Values of f of x as close as we like. As close as we like to L means, so this means, so what is the other way of saying that? It means the distance between f of x and L very small. Distance between f of x and L very small. Okay? What do we mean by values of f of x close enough to a? Values of x close enough to a but not equal to a. What does it mean? So how are we going to change that? Taking x sufficiently, so that means taking x sufficiently close to a. But of course, x not equal to a. So that's what we mean by values of f of x close enough to a but not equal to a. Taking x sufficiently close to a but not x equals a. Okay? Now let's try to get another way of saying this that we got from these two phrases. No? So when we say distance between f of x and L very small, taking x sufficiently close to a but x not equal to a, so we mean, so let's write that. So let's put that in statement. We can make the distance or or difference. So you say distance, it means difference, no? The difference between f of x, between f of x and L, very small, by taking x sufficiently close to A. But of course, x not equal to A. Okay? Now, what about distance between f of x and L very small? What do we mean by that? So, again, distance means difference. Difference between f of x and L very small. So what is the other way of saying that? So mathematically we mean that the absolute value of f of x minus L, because you want distance, so it means the difference between f of x and L, the absolute value, because you want distance, so the positive difference. So to make a positive difference, we take the absolute value. Arbitrarily small, that's what we mean mathematically. Arbitrarily really small. Okay? And what about taking x sufficiently small? So when you say taking x sufficiently small, or close to A, but x not equal to A, what does that mean in terms of mathematical form? So not equal to A, so it means the value of x and A will not be equal, because x not equal to A. So when x is not equal to A, the distance cannot be zero, unlike for f of x and L. If f of x happens to be equal to L, then the distance will become zero, possible to be zero, or positive. But for taking x sufficiently close to A, but not equal to A, we can't have the difference to be zero. Okay? So, absolute value of x minus A, sufficiently small. So again, taking x sufficiently close, so it means x minus A, the difference, the positive difference, sufficiently small. Okay? So, from here, we now make this statement from these phrases that we got. We can make, remember our goal is to come up with the precise definition of limit. So that's why we are trying to express every group of words in the intuitive definition. We're trying to express them in mathematical form, pure mathematical form. So we can make this difference between f of x and L very small. So I can now write, we can make the absolute value of f of x minus L arbitrarily small, no? Arbitrarily small by taking the absolute value of x minus a sufficiently small. Sufficiently small. But of course, remember, x is not equal to a. Since it is possible that the function f under consideration is undefined at x equals a. Okay? So that's why we do not want x to be equal to a. But remember, what we are just trying to have, your x is approaching only, no? Yeah. So, this phrase f of x minus L, the difference, then take the absolute value so that it becomes distance, no? Is arbitrarily small, arbitrarily small. What does it mean? So we mean this. Yeah. So arbitrary small. So meaning we can think of a positive number. So there is a positive number so that this difference is what? Is small, no? So it means there is a positive number. Let's say it is an epsilon such that such difference is less than or equal to this number. So that is positive positive epsilon. Okay? For positive epsilon. Again, f of x minus L, the absolute value of that is arbitrarily small, means I can think of a positive number epsilon such that this difference is less than that number. Okay? Absolute value of x minus a sufficiently small, x not equal to a. What does this mean? So for positive, let's say delta, for positive number delta, this absolute value of x minus a is less than such number. Okay? So for positive epsilon, the absolute value of f of x minus n is less than that epsilon. So that's what that line means. And x absolute value of x minus a sufficiently small, x not equal to a. What does that mean? So for positive number delta, the absolute value of x minus a is less than that delta. And since x is not equal to a, x minus a, the absolute value, is supposedly greater than 0. Okay? So from that, we can make this statement, no? So we're now close to the actual definition. We can assign. So it means from there we can assign. We can assign a positive number epsilon, say epsilon, however small, so that this difference, f of x minus L, absolute value of such, is less than epsilon. By finding, so we can do that, we can assign a positive number, say epsilon, however small, so that difference between f of x and L is less than epsilon. By finding what? By finding a corresponding positive number delta. Positive number delta for which this absolute value of x minus a is between 0 and delta. Remember, x is not equal to a. So it means it is what? And remember, absolute value of x minus a is positive. So it is greater than 0 because cannot be equal to a. So cannot be equal to 0, greater than 0. But of course, we want it to be less than such positive number delta, because I can always think of a number, let's say delta, such that this difference is less than that. Okay? So we can now simplify this. So this means, so we can assign a positive number, say epsilon, however small, so that the absolute value of f of x minus L is less than epsilon, by taking a corresponding positive number delta for which the absolute value of x minus a is between 0 and delta. So it means for any epsilon that is greater than 0, we can find a delta that is also greater than 0, such that if x is in between a minus delta, a plus delta, so meaning x is element of this open interval, a minus delta, a plus delta. If this value of x is in this open interval and x not equal to a, then f of x is in this interval, open interval L minus epsilon, L plus epsilon. Okay? So that is, if the absolute value of x minus a is between 0 and delta, then this difference f of x minus L is less than epsilon. Okay? So that's what we mean by the definition that we had intuitively. As x approaches a, the limit of f of x, if it exists, is a unique number L being approached by the values of f of x, as x assumes values arbitrarily close to a but not equal to a. So it means if the absolute value of x minus a is between 0 and delta, then the absolute value of f of x minus L is less than epsilon. See, we are able to reduce that intuitive definition in mathematical form. So we can now formally define limit of a function precisely or formally. Okay? So we have definition of limit of a function formal or precise definition. Precise or formal definition. So what we had before, again, intuitive definition. That is informal definition. So this time, formal. So let f be a function defined on some open interval containing x equals a. That interval contains x equals a, except possibly except possibly at a itself. At a itself. So meaning, on the interval containing x equals a, the value of f of x is always defined for every x that you are going to take in that open interval, except at x equals a. It is okay if the function is undefined at x equals a. But of course, if it is defined, no problem. But we don't require x to be defined there. Because remember, we want only your x to approach that number. Okay? And let L be a real number then the limit of f of x as x approaches a is L, written as limit as x approaches a of f of x is equal to L. If, so meaning this is true if for any number epsilon that is greater than 0, so meaning for any positive number epsilon, however small, gaano man kaliit yung epsilon na yan, however small, there exists, meaning we can always find, there exists a number delta that is positive such that if the absolute value of x minus a is between 0 and delta, then the absolute value of f of x minus L is less than epsilon. Okay? So that's the formal definition of limit. We can use this formal definition of limit in proving whether the given limit with f of x as x approaches a is equal to L mathematically. Okay? So graphically, so which we had already before. So this is what it means graphically. Are you still in there, guys? It's hard to actually, it's hard to explain or understand formal definition of limit. That's why we introduce it graphically and numerically for you at least to have a concrete understanding of it. Because if we begin by definition formally like this, if I begin by this, so perhaps you won't really understand what really limit is. Okay? That's why we begin graphically and numerically, because the definition formally is really mathematical and it's not easy to understand. That's why we try to replace the phrases in the informal definition, in the intuitive definition, gradually so that they becomes what? They become what? Mathematical informed. Okay? So you just go back to the corresponding implications of every phrase, no? So that you will understand really why it becomes like this mathematically. So let's say this is my A, this is my A, and this is my allowance, no? This is my interval. So that's what the definition means. There is an interval containing A. So this is the interval. And this is my x equals A. Okay? And I'm going to move away from a certain amount. What is that amount? I'm going to have delta. So it means before this endpoint, because it is open, no? So not included. So there is always a number that I can add to what? To a, but still in the interval, and that is delta. Okay? So it means here it is a plus delta, a number that is inside but close to the endpoint, to the right. And to the left, it is a minus delta. Okay? So, but this a minus delta is still inside but close to the left. So, if I'm going to, so again, this distance is delta. This is also, it's hard to make a brace sa taas ng horizontal. So this is also delta. Yan. So, and then corresponding here, so this, let's say this is L. So, there is also an interval containing L such that at the upper, we have L plus epsilon, and here L minus epsilon. And of course, these numbers L plus epsilon and delta epsilon, L plus epsilon and L minus epsilon are inside the interval, okay? And L is contained in between these two numbers. So we have the graph. So the graph is not necessarily defined or has a value at x equals a, no? In general. But of course, if the function is defined there, much better. But generally, it's not necessarily to be defined there. Let's say this is my function. That's y equals f of x. So, ang challenge in that formal definition is that if f of x, if the limit of f of x equals, as x approaches a is equal to L, no? That's what we have. So, give me a positive number epsilon. I can always find a delta that will correspond to that, no? Yun, I can always find a delta that will make your f of x to have a limit at L. So, by making your a very, very close, of course, by making your delta small. If you try to make your delta small, then it means your x is getting to be very, very close to a. So, your L is attained, no? Meaning the function will be very, very close to L, and that's the limit. So, mathematically, formal definition, that's the formal definition, and this is how we interpret this graphically, that formal definition. Okay? So, we are going to use this formal definition in proving whether the given limit is really such limit, no? So, and let L be a real number then the limit of f of x as x approaches a is L, written as limit as x approaches a of f of x is equal to L. If, so meaning this is true if for any number epsilon that is greater than 0, so meaning for any positive number epsilon, however small, gaano man kaliit yung epsilon na yan, however small, there exists, meaning we can always find, there exists a number delta that is positive such that if the absolute value of x minus a is between 0 and delta, then the absolute value of f of x minus L is less than epsilon. Okay? So, that's the formal definition of limit. We can use this formal definition of limit in proving whether the given limit with f of x as x approaches a is equal to L mathematically. Okay? So graphically, so which we had already before. So this is what it means graphically. Are you still in there, guys? It's hard to actually, it's hard to explain or understand formal definition of limit. That's why we introduce it graphically and numerically for you at least to have a concrete understanding of it. Because if we begin by definition formally like this, if I begin by this, so perhaps you won't really understand what really limit is. Okay? That's why we begin graphically and in and numerically, because the definition formally is really mathematical and it's not easy to understand. That's why we try to replace the phrases in the informal definition, in the intuitive definition, gradually so that they becomes what? They become what? Mathematically informed. Okay? So you just go back to the corresponding implications of every phrase, no? So that you will understand really why it becomes like this mathematically. So let's say this is my A, this is my A, and this is my allowance, no? This is my interval. So that's what the definition means. There is an interval containing A. So this is the interval. And this is my x equals A. Okay? And I'm going to move away from a certain amount. What is that amount? I'm going to have delta. So it means before this endpoint, because it is open, no? So not included. So there is always a number that I can add to what? To to A, but still in the interval, and that is delta. Okay? So it means here it is A plus delta, a number that is inside but close to the endpoint, to the right. And to the left, it is A minus delta. Okay? So, but this A minus delta is still inside but close to the left. So, if I'm going to, so again, this distance is delta. This is also, it's hard to make a brace sa taas ng horizontal. So this is also delta. Yan. So, and then corresponding here, so this, let's say this is L. So, there is also an interval containing L such that at the upper, we have L plus epsilon, and here L minus epsilon. And of course, these numbers L plus epsilon and delta epsilon, L plus epsilon and L minus epsilon are inside the interval, okay? And L is contained in between these two numbers. So we have the graph. So the graph is not necessarily defined or has a value at x equals a, no? In general. But of course, if the function is defined there, much better. But generally, it's not necessarily to be defined there. Let's say this is my function. That's y equals f of x. So, ang challenge in that formal definition is that um, if f of x, if the limit of f of x equals, as x approaches a is equal to L, no? That's what we have. So, give me a positive number epsilon. I can always find a delta that will correspond to that, no? Yun, I can always find a delta that will make your f of x to have a limit at L. So, by making your a very, very close, of course, by making your delta small. If you try to make your delta small, then it means your x is getting to be very, very close to a. So, your L is attained, no? Meaning the function will be very, very close to L, and that's the limit. So, mathematically, formal definition, that's the formal definition, and this is how we interpret this graphically, that formal definition. Okay? So, we are going to use this formal definition in proving whether the given limit is really such limit, no? So, the challenging part, in the precise definition, of limit of a function is when we wish to prove the limit statement limit of f of x as x approaches a is equal to L. Showing or proving, that limit as x approaches a of f of x equals L consists of two parts. Okay? So what are they? Number one, finding an appropriate delta. That's the challenge, no? Finding an appropriate delta. So we call this part preliminary analysis. Preliminary analysis. And the second part, when you wish to prove that limit of f of x as x approaches a is L, we have showing that the chosen delta works. So you have to show that this delta that you have chosen really works. So that's formal proof. So this is now the formal proof. Formal proof. Okay? So let's do that. So let's say you are asked to prove that the limit of 3x minus 2 as x approaches 2 is equal to 4. So using delta epsilon definition. By the way, the formal definition is sometimes called delta epsilon definition of limit of a function prove that number one, limit as x approaches, let's say 2, of 3x minus 2 is equal to 4. Okay? Of course, if you have had idea of calculus when you were in senior high, so, but I assume that none of you took that, no? Calculus in senior high. So you say that you simply have 3 times 2, that is 6 minus 2 equals 4, but that's not proving. When you say proving, you have to show that the condition in the definition of limit of a function is satisfied. Okay? So, this is how to prove it. So, proof. So, you write there proof. You don't just solve and solve, huh? So, you have to follow the proper way of proving, because this is proving. So, let epsilon be positive, and that is given, no? Let positive epsilon be given. Let's say that is given, no? Yan. We want to find a delta that is positive such that if the absolute value between x minus a and is between delta and between 0 and delta, then the absolute value of f of x minus L is less than epsilon. So this is what we want to prove, no? You have to show that. But what is our A? So that is, so we have if the absolute value between x and a. So what is our a here? Our a, we have to solve for x. So assume you equate it to 0. Now to solve for x. What is that x? So again, you have to express what you call this? We have to express we have to find a, I mean. Our a is we have to find a. Our a is this number. X approaches a. So it means our a is 2. And that is supposedly less between 0 and delta, the absolute value of x minus 2. Then, what is our L? Our L is 4. This is our L. Our L is 4. Less than epsilon. And this is what we want to prove. Okay? Now, to show that this is true, this statement is true, we have to follow the suggestions here, the 2 parts that we have to do. First, you have to find an appropriate delta and show that such delta works. Okay? So that's the challenge. Okay, so first step, find an appropriate delta. Find an appropriate delta. Okay? So how to find an appropriate delta? Note that the absolute value of 3x minus 2, so that's what we have here. This is our f of x minus 4. This is f of x minus 4 minus L. Again, this is f of x. This is L. Okay? So this is f of x. This is L. So less than epsilon. So we can express this. So this is equivalent to what? Remember, we're trying to find delta. Okay? So we know that delta f of x minus L, that is the absolute value of that, so is less than epsilon, no? So that's what actually what we want to prove. But this is equivalent to what? To factor out 3, because we are trying to find delta. So we have to express this in the form of x minus a to find that delta. So x minus, this is minus what? Minus 2, no? Absolute value of such. Y. So remember, 3x minus 2 minus 4 means what? Means 3x. I will write it first so that you will not be confused. Simplify first. So it means 3x minus what? Minus 6. Okay? And this is equivalent to what? So that is further equivalent to, if I factor out 3, I will get x minus 2. Okay? And then, if I factor out, take the absolute value ng factors ng product, absolute value ng 3 is 3. Then, times the absolute value of x minus 2. Okay? Remember, this is less than epsilon. Less than epsilon. Less than epsilon. I can now solve for x minus 2. So by dividing what? By 3 each side. If we divide by 3, we get epsilon over, so we have absolute value of x minus 2 is less than epsilon over what? Over 3. So this means that our delta is epsilon over 3. Thus, we can choose that, we can choose delta to be what? To be equal to epsilon over 3. Remember, we have x minus a is less than delta. So this is our delta. So this is our delta. Okay? So our delta is epsilon over 3. Actually, we can choose any delta that is less than epsilon over 3. Any delta that is less than epsilon over 3, you can also what? You can also use. But of course, since we do not know the actual value of epsilon, so let's stick to this, okay? Epsilon over 3. Now, we know already the delta. So let's see if this delta, the chosen delta, will really work. If this delta will really work, then this is really true. So meaning we have to verify that this is really true. So that's what we want to prove. So again, we want to prove that this delta works on this statement. If this is true, so we have to show that this is also true. Meaning we have to show that the absolute value of f of x minus 4 is less than epsilon. Okay? For the chosen delta. So what is our chosen delta? Our delta is epsilon over 3. So we begin with what we know. This is what we are given, the hypothesis. Okay? Or the premise. We're given the premise that the absolute value of x minus 2 is between what? It between 0 and delta. Okay? That's the premise. So this implies what? I can multiply each side by 3. So if I multiply by 3 this, so I will get what? 3 times absolute value of x minus 2 is less than 3 times delta. Okay? So, but this is, this implies what? The absolute value of 3, I can put the 3 out because this is positive. It will not affect if I multiply it inside. So I have x minus 2. Okay? So that is less than 3 delta. This implies that I can multiply this inside, which is 3x minus 6. Okay? And that is less than 3 delta. And I can write this in the form of what? In the form of f of x minus 4. But what is our f of x, guys? So let me write it here. Our f of x is 3x minus 2. So meaning, this is 3x minus 2 minus L. But what is our L? That is 4. This is what I want to what? I want to show. I want to come up with this conclusion or a consequent, no? Hypothesis, conclusion. This is the hypothesis and I want to come up with this. So this is 3x. But 3x minus 6, I can write that as 3x minus 2 minus 4 because negative 6 means negative 2 minus 4. Okay? And remember what is delta? That is epsilon over 3. And this is what? Absolute value of 3x minus 2 and then minus 4. And that is less than epsilon. So that's it. So since from this hypothesis, we are able to come up with absolute value of f of x minus L less than epsilon, so it means this is really true. So we have shown that this absolute value of f of x minus L is less than epsilon, hence limit of 3x minus 2 as x approaches to is really 4. So that's it. That's the formal proof of that of this statement. Okay? So we say that, so therefore we say that limit as x approaches 2 of f of x, so that is, what is our f of x? 3x minus 2 is equal to 4. Okay? Now, formal definition is not, as I said, it's not really easy to understand, no? Especially the proving of this, you won't really appreciate because it needs a strong background of inequality. If you don't understand inequality, so you won't really appreciate this, no? So that's why this is in engineering and in other fields that that are not really close to BS math. So this is not really discussed, no? Or being discussed but not included in the test. Okay? This is just formality or for completeness. We discuss this formal definition. Okay? Let us have last one. I will not include this in the test. Who knows, once you understood this definition, you will come up with a strong understanding of limit and you will come up with applications of this in real world. Number 2. So let's say we have Are you still alive, guys?
Yes, sir.
So number 2, we have, let's have one quadratic. Limit as x approaches 2 of, as x approaches negative 1, limit as x approaches negative 1 of x squared minus 2 is equal to negative 1. So again, proof. So let positive epsilon be given. So when you say positive epsilon, epsilon that's greater than 0. Let that be given. We want, we want to find a delta that is positive such that if the absolute value of x minus a, what is our a? Negative 1. X approaches a. So our a is negative 1. So absolute value of x minus a is between 0 and delta. Then, the absolute value of f of x minus L, what is my f of x? X is squared minus 2. That's my f of x minus L, negative 1.
Negative 1.
Also, no? So, that is less than epsilon. Or equivalently, let's simplify this. If the absolute value between x and a, difference between x and a, so that is x plus 1 now, no? When simplified, less than epsilon, then we have x squared minus 1. Is that correct? Right? So, minus 1 less than epsilon. Ay, sorry. This is epsilon, no? This is epsilon. So, this is what we want to prove. That is statement. So, with this hypothesis, if this is true, then we have to show that this is also true. But the challenge is to find that delta. How to find that delta in terms of epsilon? So this is how to find, of course. So first step, finding the appropriate what? Delta. Finding an appropriate delta. Appropriate delta. What is that delta that is that can work, no? So that this becomes true. Appropriate delta. Still joining or leaving? So we now have, again, we get it from here, from the f of x minus L. So let's try to get it from there. We know that x squared minus, note that, so note that the absolute value of x squared minus 1 is what? Is less than epsilon, no? And equivalently, so we have absolute value of x plus 1, x minus 1, when factored the inside. So absolute value of x minus x plus 1, x minus 1. So that is less than what? Epsilon. So further equivalently, so that is equivalent to, so we are just trying to rewrite this, no? So that we will come up with the nice delta. So, para pag nag-prove tayo formally, it will really work. Yun yung technique. So, that is the absolute value of x minus 1. Let's start with x minus 1. Then times the absolute value of x plus 1. After all, commutativity holds, no? Absolute value of x minus 1 times absolute value of x plus 1. And that is less than epsilon. Okay? Now, how to find that delta from there? So we want to bound x minus 1, no? We want to bound this x minus 1, meaning absolute value of x minus 1 is less than what number? That's what we try to find. So, meaning, what will be the best replacement for this so that it will be less than a certain positive number, no? That we are looking for. Since we want our x to be close to negative 1, remember, our x, we want it to be close to negative 1, right? So we are going to restrict the distance between them to be within 1. So at least not greater than 1, no? So that it is really close to negative 1. To be really close to negative 1, we want our x to be close to negative 1. So that is, the distance between them is at most 1. Okay? So that's what we want. So let's bound again. Let's bound. And let's bound absolute value of x minus 1. This is what we want to bound, no? So again, we want your x, we want x to be what? To be close to negative 1. To negative 1. So we want your what? You want your interval to be centered at negative 1, and when you add a certain number, a certain delta to negative 1 to the right, and then you subtract it from negative 1, so meaning to the left, so that is within 1, the difference, no? So within 1. So we want, so that is, we want our delta, we want our delta to be within this. Okay? So that, the absolute value of x minus 1, x plus 1 is less than epsilon, and delta is within or at most 1. Okay? So we're trying to find an equivalent to this so that I can maintain x minus 1 and I have a value of epsilon in terms of delta, because that's what our goal is. Okay? So how to find a replacement to x plus 1? No? So let's see. So this implies, this line implies what? Implies 0 between is less than absolute value of x plus 1, and that is less than 1. Okay? And this is equivalent, this implies that out of this I can get, if I remove absolute value between these. So absolute value of x plus 1 is less than 1 means negative 1 is less than x plus 1 is less than 1. Again, if I have absolute value of a, that is equal to, let's say, rate less than a certain number na positive, let's say 2. It is equivalent to a is between negative 2 and positive 2. Okay? So that's how I write without absolute value. Still joining? Let me erase this now. So again, if I remove absolute value less than 1, so it means x plus 1 is less than, is between negative 1 and 1. I can manipulate this to come up with what I want. Because I want to, remember, I want to bound x minus 1. So I want to find the, the expression, the number that is less than this, no? I mean greater than. This is supposed to be greater than what? So I want to express that in that form. So negative 1. So I have to remove what? I have to make in the one that is in between, I want to make it negative x minus 1. How to convert this to x minus 1? I have to add negative 2. So if I add negative 2 in its part, less than 1 plus 2, so I get negative 3 less than x minus 1 less than 3. Okay? I'm sorry, it is, am I right? So this is, sorry, it is plus negative 2, no? Sorry, plus negative 2. Negative 2. So this is negative 3 less than x minus 1 less than negative 1. Okay? Okay, guys? But this is equivalent to, this is equivalent to absolute value of x minus 1 is less than 3. In inequality, if I take the absolute value of this, it is less than 3. Okay? So again, this I can get from this inequality if I take the absolute value of this. So, if x minus 1 is greater than what? Is greater than negative 3. So, if I take the absolute value, it is greater than what? The absolute value of negative 3, which is, I mean, it will become less than 3. Okay? The absolute value of that. So, again, taking, the problem here is that if you have a weak background of inequality, no? If you have a weak background of inequality, it's not easy to understand the equivalent in terms of inequality. Yan. So again, if I take the absolute value of x minus 1, then it is less than 3. Okay? So like for instance, if I have 5 x minus 1, this is negative 3. Let's say I have this. Negative 3 is less than x minus 1. Okay? Yan. That one, I'm interested with this. So, if I'm going to, of course, it is less than 1. Okay? It is less than, if it is less than 1. So, meaning, it is in between 1 and 3. It is in between 1 and 3. If you take that, it is between 1 and 3. It will become between 1 and 3. So, mag-change ang position. But what we want is, but guaranteed, it is less than 3. Okay? So, it is less than 3. It is between that, but I can say that it is what? Less than 3. Okay? Now, from here, yan. So, it means this is my what? This is my replacement here, no? So, I can now have this statement. Hence, we get absolute value of x minus 1 times absolute value of x plus what? Plus 1 is less than absolute value of x plus 1. But if x minus 1, absolute value of x was x minus 1, absolute value of x plus 1 is less than, so, but this is less than 3. So meaning this is less than 3. If I replace this by 3, this is now greater than this product. So again, absolute value of x minus 1 is less than 3. This is less than 3. Times this, so times this. If I replace this by 3, this product now is greater than this. Because remember, this is greater than 3. This is 3. This 3 is greater than this. So if I replace this by what? By 3, this product now is greater than this. Okay? Yeah. So that's the hardest thing, part of such, no? Again, this is less than 3, this quantity. Yeah. So that this is now true. Okay? So from here, so this is supposedly less than epsilon, right? This is less than epsilon. Okay? Remember, this product is what? Is less than epsilon, and this is less than this product, and this is less than epsilon also. Okay? Yan. So, I can now replace this. So, this is now this one. And equivalently, this line. So, did you get that, guys? This is less than epsilon, but this is less than 3, absolute value of x plus 1, and that is less than what? Epsilon, okay? And I can divide this by 3. So, I now get, nagkataon lang, epsilon over 3 also, ha? So, you have to choose, delta to be what? To be smaller, to be the smaller of 1 and delta, epsilon over 3. Remember, we have another condition. Epsilon is less than or equal to 1. If this happens to be greater than 1, you are going to choose 1. If this happens to be less than 1, you're going to choose epsilon over 3. So, which means, so this we write as minimum of 1 delta epsilon over 3. So this means minimum of this. So when you say minimum of this, you choose between 1 and this, whichever is smaller. Okay? So let's see if this will work. No? Let's say we try this one. So you have to show that this epsilon over 3 works. So let's see if this really works. We have less than 0 is less than absolute value of x plus 1, less than delta. So this is our premise, no? So let's see if we will come up with this. So with this, if then. So let's see if we will come up with this. So that is, so we have to express this as this less than epsilon, delta, and also we want your x minus 1 to be less than 3. Okay? And this means x minus 1, absolute value of x plus 1. But what is this? So, since absolute value of x minus 1 is less than 3, so I can have it less than 3, what? Delta. So, this product is less than 3 times delta. Is less than that. Because this is less than delta and this is less than 3. So, the product is less than 3 times delta. Okay? Now, from there, I can express that as 1 absolute value, x minus 1, x plus 1. This product I can express as 1 absolute value. So, product of absolute value of x minus 1, x plus 1, that is less than 3, delta. And I can multiply this, so this is x squared minus 1, and that is less than 3 delta. But I can express this absolute value as x squared minus what? Minus 2. But if I subtract minus 2, I have to add plus 2. So, minus 1 plus 2. Because I subtract 2. Less than, but I know that epsilon is, delta is epsilon over 3. So this is now what? So we're almost done. X squared minus 2 and then plus 1 or minus negative 1. So this is what we want, no? And this is epsilon. If we go back to the statement, to the conclusion that what we want, so this is the conclusion that we want. Okay? So, yan. X squared minus 1 is less than epsilon, or x squared minus 2 minus negative 1 is less than epsilon. That's it. So, it means we were done, no? Yan, we're done. Actually, we can stop right here if you want, because this is already what we had in the simplified form. Here. This is equivalent already here. So, it's alright to stop right here. Okay? So, let me cut this. I can stop right there. And then, replace this by epsilon over 3. And that is less than epsilon. And this is what we want to get. Therefore, we say that the limit as x approaches what? Negative 1 of x squared minus 2 is really equal to negative 1. Okay? So that's it. So we're done, no? We're done. So when you're proving, by the way, you put what you call this? An end to the proof. So you put a box. So it means it's an end. Or a smiley if you want. Or a smiley. So it means you're done. Okay? So that's how formal definition is used or being applied. It is just used in proving whether a given limit is true or not, no? So a given limit is statement. But I'm not going to give you a test on this. I touched of this just in case, who knows, one of you might be interested and go further about this and have an application. Yeah. So that's the formal definition of limit. So if you're going to ask yourself, of course, you better go to the intuitive approach, no? Because you can easily understand the intuitive approach. But mathematically, the intuitive is not really accepted, no? It is accepted the formal proof. I mean the formal definition. And that is the, the accepted one. Now let's now begin with algebraic techniques of finding limits. Do you have any question with that, guys? So you have to recall your your inequalities. It's not easy to explain or to you at this point in time such inequalities, no? If you do not have strong background of inequalities, I tell you, you won't really appreciate. Perhaps some of you are already sleeping. So many students are sleeping when it comes to these topics. So only those BS Math who are interested with this. You know, BS Math, they really want something like this. They want always probing, no? They are not satisfied if they don't see the mathematical proof. So we now move to algebraic techniques. This is the exciting one, which I think you won't be excited of also because it requires a lot of algebra this time. So algebraic techniques or approach of finding limits. Techniques of finding limits. For finding limits. Yan. Now, instead of verifying using limit definition, formal definition, we're going to have the following theorems on limits. Now, these theorems are verified by what? By the definition, formal definition of limit. The reason why we come up with this, and these are being used because they are proven true. Using what? Using formal definition. So, the following are the theorems on limits, no? Yeah. Let's have the following theorems. Theorems on limits. Let f and g be functions by the way, are the people from other section here? That's why I want it to be taught once only, is because if I'm going to teach you 7:30 to 10 a while ago, so imagine I am going to repeat this again. I'm going to repeat, I mean. So that's why I ask you to join if you are free. So let f and g be functions for which limit as x approaches a of f of x and limit as x approaches a of g of x both exist. Let us assume that they both exist and equal, for instance, to L1 and L2 respectively. And let's see be any constant, be a constant. Then we have the following theorems. Then the following theorems hold. Then the following theorems hold, meaning are true. Number one, limit of a constant. Limit of a constant. If you have a constant and you take the limit of it, limit as x approaches a of a constant, let's say c, it is still c. There's no effect, no? the limit of a constant is equal to that constant as x approaches to any number. The second theorem, limit of a sum or difference of a sum or difference or difference. If you have a sum or difference of functions, how to get the limit? So we have limit as x approaches a of, let's say, f of x plus g of x, that is equal to limit of the first function plus limit of the second function. You can get the limits individually of the terms, no? So that's what the theorem is saying. If it is difference, then you just get difference of their limits. So limit of a sum or difference is equal to the sum or difference of their limits. Number 3. Again, take note of this. I can split this into sum of limits provided the limit of f of x and limit of g of x both exist. If they don't both exist, so you cannot split that sum. Okay? You have it as is. Take a limit of that sum. You cannot split into sum of limits. Then we have limit of a difference of functions. Sorry, limit of constant multiple because we had already the difference, no? Sorry. Limit of a constant multiple of a function. Of a constant multiple of a function. What do we mean by this? So we mean limit as x approaches a of constant times f of x. So that's what we mean. If you have a constant multiplied to a function, you take the limit. So that is equal to the constant multiplied to the limit of f of x. Yan. You can put the constant out without affecting the limit. Okay? Let's say, number 4. Number 4, we have limit of product. What about for product? If you have limit of product, limit of a product of functions, we have limit as x approaches a of f of x times g of x. So let's say I have product of functions. What is the limit of such product? It is equal to the product of their limits. No? You can split into product. Product of f of x times, product of limit of f of x and limit of g of x. So again, limit of a product is product of the limit. Limit of a product of functions is equal to the limit of the first function times the limit of the second function. What about quotient? limit of quotient, limit of a quotient of functions. For limit of a quotient of functions, we have limit as x approaches a of f of x over g of x. And this is equal to quotient of their limits. Okay? Limit as x approaches a, f of x as x approaches a over limit as x approaches a of g of x. Provided, limit here, provided limit of g of x as x approaches a is not equal to 0. So meaning you cannot split this quotient into quotient of limits if the denominator's limit is equal to 0. Okay? So that's what it means. Do you understand, guys? What it means? Guys? Hi, guys. So these are the theorems on limits that we're going to use. Yes.
Hindi na po ba abot sa yung di ba po may power ba and then root of
Meron pa. That is mga basic pa lang. Nasa ano pa lang tayo? Nasa theorems o hanggang 5 pa lang. Marami pa yan. May radicals pa. Okay? Number 6, I'm just asking you. Did you understand, guys? So let's have number 6. We have limit of a power of a function. Now, if I have, let's say, a power, limit, as x approaches a of f of x, and this f of x is raised to, let's say, n, this is equal to limit as x approaches a, limit of f of x as x approaches a raised to n. So again, limit of a power is what? Is equal to limit of the base of the power here raised to n. So I can raise the limit of f of x to n, no? So you will get the same. Okay? So where n here is a positive integer. Okay? So we assume that n is a positive integer. And then the last one, we have number 7 for algebraic functions. No? So later we'll have involving trigonometric. Limit of, is it 7 or 8 now? The numbering.
7 po.
Sa ulo ko lang kasi, pero hindi ko alam numbering. Limit of a root of a function. Of a function. You have to be careful when dealing with limit of a root. If I have, let's say, limit of a root, meaning nth root of, let's say, f of x, nth root, as x approaches a, I can have it nth root of limit as x approaches a of f of x. Okay? But take note where the order or the index is supposed to be even if the limit inside is what? Is positive, no? Now, if let's say the limit inside is not positive or it is equal to 0, we require n to be add. If n is even and inside is, the limit inside is 0 or negative, that theorem does not work. So, where limit as x approaches a of f of x is supposed to be positive if n is even. Again, if n is even, we require for the limit inside to be positive. If the limit inside is 0 or negative, if n is even, the theorem does not work. Okay? So even it is 0 if n is even. If it is cube root, no problem. The limit inside can be any number. Is that clear, children?
Yes, sir.
Okay. So let's now begin. Evaluate the following. We're going to begin, by the way, with evaluation of limits. Those dealing with limits without problems, no? So, limits of functions with no problem at x equals a. Okay? Yeah. With no problem at x equals a. So meaning, the value of the function is defined there and the function is defined at every number in the interval x equals a, containing a, no? No problem with at x equals a, and f of x is defined at every number in the interval containing what? Containing a. Let's say x sub 1 and x sub 2 with a belongs to that limit, that interval. Every number inside this interval, of course we don't include the endpoints, at every number in this interval, open interval x sub 1 to x sub 2, and this interval contains a. So meaning, the function value is also defined at x equals a, no? So, and at every number in between this. So, guaranteed that there is no problem for the function in this interval. So, you can always use the limit peacefully, with peaceful mind. Okay? So, you do not have to worry about any problem. It's just like evaluating a function. So, again, if this is the case, in this case, limit as x approaches a in general of f of x is simply equal to f of a. Okay? So the function value is equal to, at x equals a, is equal to the limit of f of x as x approaches a. If you have this condition, no problem at x equals a, and the value of the function is defined at every number that you can find in the interval x sub 1, x sub 2, in that open interval that interval contains x equals a. So it's just like what? Evaluating function. You can just simply substitute, meaning you can simply substitute a to x. Okay, in finding the limit in the following example. Evaluate the given limit. Is that clear, guys? Number 1. So, limit as x approaches, let's say, negative pi plus 3. Is negative pi plus 3 a constant, children? As x approaches 4. Guys, is negative pi plus 3 a constant? Yes. Therefore, the answer is negative pi plus 3. Number 2. Limit as x approaches negative 1. For instance, I have 5x to the 4th plus 1. So, I can simply write what? No need to split. I can just have it 5 times negative 1 raised to 4 plus 1. It's just like evaluating a function. Okay? Because negative 1, there is an interval containing negative 1 such that the function 5x to the 4 plus 1 is always defined at every number in that interval. Let's say negative 2 to negative what? Negative 2 to negative to 0. That negative 2 to 0 contains what? That interval contains negative 1. At every number in between negative 2 and 0, the function 5x to the 4 plus 1 always defined. Okay? Number 3. Of course, this is not exciting, no? Because it's just like evaluating function value. So, 4x cubed plus minus, hindi ko masulat yung trinom, minus 10 all over x squared plus x. Yan. Okay? When you are evaluating quotient, always make it a habit to check first the denominator. If the denominator, the limit is 0, then you have to pause and do not evaluate it immediately, no? Do not substitute immediately your x equals to, you cannot apply this. This limit of f of x as x approaches a is equal to f of a. Okay? You cannot apply that. Because this condition is not satisfied. I mean, the condition here. So, in this case, see, 4 plus 2, okay. So, 4 plus 2, okay. So, in the numerator, 4 times 2 cubed, and then minus 10. What is that equal to? 4 times 8?
22 over 6.
22 over 6. What is that 22 over 6? 11 over 3. Okay now, guys? No, I'm not going to go into detail anymore, limit of everything, no? So after all, there is no problem. So just actually to illustrate those theorems, you have to write limit of the quotient, limit of the 4x cubed minus 10 over limit of x squared plus x, and then limit of the individual terms, and then apply power. So I assume that you understand already this theorem. And after all, these functions do not have problem on a certain interval containing 4, negative 1, and 2 respectively. On number 4, what about if I give you something like this, no? Something na medyo medyo iba ng konti, no? Later, yung mga may at least transcendental. As x approaches, let's say, negative 2, approaches negative 2, yeah. Then 2x minus 1 all over x squared minus 3 quantity squared. Yan. Okay. So we now have what? So I can just have substitution, no? Because the denominator does not have a problem there. Or the denominator is 4 minus 1, no? So negative 2 quantity squared minus 3 in the denominator. In the numerator, that is what? 2 times negative 2 minus 1, no? And then we have to square this. What is that equal to? This is negative, so 25 over 1. 4 minus 3, 1. So it is 25 pa rin, ah? Is that correct, guys? Okay. Number 5. Limit as x approaches, let's say, a negative 1 of x squared plus 8 all over, this is the radicand, 22 minus 3x cubed. This is equal to. Let's check the radicand. What is the denominator? 22 minus 3 times, it is not 0, no? It's not 0, the denominator, okay. But if let's say you got a number that is, let's say you got 0, you have to revise your solution. You have to cross it, it's wrong, no? To evaluate immediately. What is the numerator? 3. And the denominator? So it's not 0. Since it's not 0, I can apply the theorem, no? And then this is simply substitution rule. So we have negative 1 quantity squared plus 8 all over what? 22 minus 3 times negative 1 raised to 3. And that is equal to square root of, ano yung numerator? 9. 9 over 25. And that is equal to what? What is that equal to when simplified? Square root of 29 over 25. 3 over 5. Okay now, guys? Okay? So what about this one? Number 6. Limit as x approaches 2 of the absolute value of x minus 7 all over cube root of 4 x squared minus 8. Okay? So this is equal to? So this is absolute value of 2 minus 7, no? What is that? 5. What about the denominator? Cube root of 4 times 4, 16, no? Minus 8. And that is equal to 8. Cube root of 8, 2. Is that correct, guys? Okay? 7. Limit as x approaches, let's say, pi over 4 of tangent x all over sine squared x plus 7. What about that? So tangent pi over 4 is okay, no? that is equal actually to 1. Sine pi over 4 is also okay. That is equal actually to square root of 2 over 2. Then plus 7. This is equal to 1 over, what is sine pi over 4? Square root of 2 over 2. So that is quantity squared. Okay? And then plus 7. What is square root of 2 over 2? 1/2. So times 2. So this is equal to 2. This is 1/2, no? Times 2, 4. 4 plus 14, what is that? What is 4 plus 14? Because I multiplied by 2. I multiplied by 2. By the way, it's just, sorry. This is 1 over square root of 2, 1/2 times 2, 1. 1 plus 7, 1 plus 14, I mean, 15. Okay. Am I correct with the simplification, guys? I multiply the numerator by 2, I multiply the denominator by 2. So 2 plus 14, the denominator. 2 over 2 means 1, so it will not affect the value. Okay now, guys? Okay, guys. Is that correct?
Sir, I think it's 1/2.
Yeah, it's 1/2. 1/2 here. 1/2 plus 7, when multiplied by 2 over 2, it is 2 over 1 plus 14 is 15. It's 1 over 1/2 plus 7 times 2 over 2. That is 2 over 2 times 1/2 is 1 plus 14. So that is 2 over 15. Okay now, guys? Okay, guys. Okay. So, next number, let's have this time we deal with those with problems, no? Limits having problem, okay? This time limits with problems at x equals a. Limits with of functions where functions have problem, where functions have problems with what? Problems with x equals a. Yung limit ang function na nag-approach sa a, but the functions have problems at x equals a. Like for instance, x over x minus 2, let's say x approaches 2. So the denominator becomes 0. So the function has a problem there. So what about the limit? How can we handle the limit if a function has a problem at x equals a? Okay? So let's have the following examples. By the way, if you have a problem like this, one solution is using this theorem. So the following theorem will help. So there is a theorem here that can handle this. No? Let A be a real number. Let A be a real number and let f of x equals g of x, let f of x always equal to g of x for all x, as long as x is not equal to a. These are always equal, the values of f of x and g of x, for x not equal to a. Other than a, these are always equal, the f of x and g of x. So, in an interval, in an open interval, containing what? Containing a. And that is our condition. If the limit, for instance, as x approaches a, of f of x, I mean g of x, let's say g of x, g of x. Let's say the limit of this exists. Then, the limit of f of x as x approaches a also exists. And limit as x approaches a of f of x is equal to what? The limit as x approaches a of g of x. So again, let's say the limit of g of x exists, and it so happens that f of x is always equal to g of x, as long as your x is not equal to a. They are always equal except at x equals a. So if the limit of g of x as x approaches a exists, then the limit of f of x as x approaches a also exists, and they are equal. Okay? So this is useful in dealing with limits that have problems at x equals a. The functions have problems at x equals a. So instead of finding the limit of the original function, we find the limit of the new function satisfying this theorem. Okay? And that is very useful in the following examples. Evaluate. So instead of evaluating the limit of the original function, we're going to evaluate the limit of another function having the same limit with the original, whose limit is not obvious, but the new function has an obvious limit. Number 1. Let's say we have limit as x approaches -2 of 2x squared plus x minus 6. So I have to think of a problem in the denominator. So x squared, I want to have it a problem at -2. So plus 5x plus 6 yan. Okay, evaluate this limit. Now, if you have a limit of a quotient, don't be excited to substitute immediately function values. To substitute immediately -2 to x. Because many students are excited substituting it immediately, but without realizing it has a problem, okay, in the denominator. So first, check the limit of the denominator. So it's not a case like what we had before, that there is no problem at x equals -2, the given function. So at x equals -2, the denominator is what? Let's take the limit of that. Yeah. So, of the denominator first. So the denominator is a polynomial. It has no problem and at any number. So we can apply substitution rule here. This is -2 quantity squared 4, -10, positive 6. We can apply here what we had before. So this is giving 0. You see, there is a problem. You cannot substitute immediately. Meaning, we cannot apply substitution rule because the denominator is 0. Okay? The limit of f of x as x approaches a is not equal to f of a in this case. So you have to take also the limit of the denominator. If the limit of the denominator is also 0, then the limit may exist. Possible that the limit may exist. The numerator is also what? Is also polynomial. So there is no problem if it is a polynomial. So you can apply substitution rule. So 2 times 4 plus negative 2 minus 6. 8 minus 8, that is what? That is also 0. Hence, we have what we call indeterminate form. So hence, the limit of 2x squared plus x minus 6 all over what? X squared plus 5x plus 6 as x approaches negative 2. I will write first the detailed solution in number 1, but next time we can have it shortcut. No? Now, takes the indeterminate form or has an indeterminate form. Has an indeterminate form. Indeterminate form. Ano daw indeterminate form? 0 over 0. If you have a form of 0 over 0 for the limit, we call that indeterminate form. Actually, that is not the only indeterminate form. That is just one possible form for indeterminate. So, pag indeterminate form, limit may or may exist. So, let's find another function whose limit is obvious, but equivalent here as long as x is not equal to 2. Equivalent to this function. So we now write limit as x approaches negative 2 of 2x squared plus 2x, plus x, minus 6 all over x squared plus 5x plus 6 now. We know that this is of indeterminate 0 over 0. Do not put equal 0 over 0, equal 0 over 0. 0 over 0 is not a number. It is a form only, a special form which is called indeterminate form, but it's not supposedly equal to this limit. So if you put equal, instead of 0, I will put you negative score. Okay? So like in the solution of some of your classmates, putting equals does not exist. Some of you put equals does not exist. So I put negative score instead of just 0. Let's say limit equals does not exist. So I put what? Limit, for instance, as x approaches 1 of x over x minus 1. Let's say equals does not exist. Instead of 0, the score negative. So remember, you should write just limit does not exist, no equal. We agreed on that. So again, also here, do not write equal 0 do not write. So do not write equal 0. Like here, do not write like this If you write like this, equals 0 over 0, wrong. Okay, negative the score. So because if I will not put negative, you won't remember. You will always do that. You will see that in many books, in Filipino books, but that is wrong. They are not very careful. Imagine if this is 0 over 0 equals. Why do you have to solve? If it is equal 0 over 0, and that's it already. Because you say it is equal to 0 over 0. That's already what you want. But 0 over 0 is not a number, so that's not what you want for the limit. So you just write there, semicolon, it means this takes the form of 0 over 0. So we now proceed. So limit. I can factor the numerator and denominator. If the numerator becomes 0 when x is negative 2, So it means there is a factor x plus 2. So guaranteed there is x plus 2 here. If it is x approaches 2, x minus 2. If x approaches negative 2, x plus 2. And then you have to find the other factor. So guaranteed there is x plus 2. So here, what is the other factor? 2x minus what? Minus 3. Is that correct? And then here, we have what? X plus 3. Yeah. From which we can now cancel. We are allowed to cancel x plus 2 because x equals is not equal to negative 2. Remember, x is just approaching to 2. To negative 2, I mean. They are not equal to, x is not equal to negative 2. So they can cancel that. And obtain another function simpler than this, but whose limit is obvious. Perhaps, no? So I now get 2x minus 3 all over x plus 3. So this is a function equivalent to this original function, but with the condition that x is not equal to negative 2. Okay? So I can now find the limit of that. I think the numerator and the denominator is no longer 0. So I can just write here equals. Substitution now works. Substitution rule. Negative 2 minus 3 all over. Let's say it's still 0 over 0. So you don't continue. You find another function until you get not 0 in the denominator. If you cannot avoid that the denominator is 0, so the limit does not exist. So this is negative 2 minus what? Minus negative 2 plus 3. And what is the answer, children? Huh? Negative 7.
Negative 7.
Yan. O, did you understand now, guys? O, number 2. Let's see if we have for number 2. Limit. Most of the limits that you will be encountering like this, not the one with no problem, because it has, if the limit has no problem, it's not exciting to deal with that. Approaching 1. So 2x cubed minus 7x squared plus 8x minus 3 all over x squared times 2 plus x squared. It's supposed to be cubed. Cube, yeah, 2x cubed plus x squared minus 8x and then plus 5. Again, be careful because this is quotient. Try to examine first the denominator. So what's the limit of the denominator? Try to have it in a scratch first. What's the limit of the numerator? What's the limit? And limit of the denominator? The denominator goes to what? Goes to 0, right? 2 times 1 plus 1, 2 times 1 plus 1, plus 8 minus 5. So, again, 2 times 1 plus 1 minus 8 plus 5. So, that is 0. The numerator, I think 0 also. 2 times 1 minus 7 plus 8 minus 3. Ayan, that's the shortcut. Instead of individual limits like what we had in number 1, you try to do not substitute immediately, ha? If you substitute and you get 0 over 0, that's not correct, no? You do it separately, the limit, like this. Or you do it like what? Like this one. So the numerator approaches 0. The denominator approaches 0 also. So it means it is an indeterminate form. Anong indeterminate form, children? 0 over 0. So let's factor that limit as x approaches 1. Guaranteed there is a factor x plus minus 1. All we have to do is to find the other factor. What's the other factor, guys? The denominator is also x minus 1, one of the factors. you are going to divide, no? Okay? Divide synthetically. Magdi-divide tayo synthetically, ha? Then I will be erasing this. So, 2, negative 7, 8, negative 3, so we have approaching 1, so minus 1, so 1 here, no? Kung ano yung approaching 1, yun nilalagay nyo. Kasi x minus 1 is one of the factors. Mabilisan. 2, 1, 5, 2, negative 5, negative 5, 3, 3, 0. So the other factor, 2x squared minus 5x plus 3. Yan. That's the other factor. Okay? What about in the denominator? 2, 1, negative 8, 5, 1 also. We have bring down 2, then 2, 3, 3, negative 5, 5, negative 0. So we have 2x squared plus 3x minus 5. Okay? So that's it. I'm going to erase that now. I will be sending to you the video recordings. So this is equal to, what is that equal to, guys? Limit as x approaches 1 of simply 2x squared. I can cancel x minus 1. After all, x is not equal to 1, right? Minus 5x plus 3. It is just approaching 2x squared plus 3x. Remember, there is, again, denominator. You have to check the status of the denominator. Let's see if this is not 0 anymore, the denominator. 2 times 1 plus 3 minus 5. Again, it's 0, so you cannot substitute immediately. You cannot apply substitution rule. This is 0. This is 2 minus 5, negative 3 plus 3, so 0 also. Again, indeterminate form. Indeterminate form. So we try to factor that at once more. Simplify. You find another function na may obvious limit. Yung nahahanap nating function, hindi pa rin obvious ang limit. Try to find another one. Ano ang factor form nito? Meron pa uling x minus 1 yan. So, ibig sabihin, that means the factor is x minus 1 quantity squared originally, no? Kung na-detect agad natin. What is the other factor, guys? 2x minus 3. The other one, 2x plus 5. Yan, plus 5. Negative 2, positive 5, positive 3. Negative 2, negative 3, negative 5. Okay. So, this is now equal to limit. Yan. As x approaches 1 of 2x minus 3 all over 2x plus 5. Yan, we can now find the limit because the denominator is no longer 0. We can apply substitution rule now. 2 times 1 minus 3 all over, guys, 2 times 1 plus 5. What's the answer? Negative 1 over 7. Okay?